Okay, great. Okay, so today I'll talk about the paper that I just posted on Archive. I literally prepared those slides last night, and I'm sure there'll be some typos, but hopefully I'll be able to explain the main ideas. Um, Now the idea is to come up with a framework that will allow us model physical biological machine learning system, and this is what we do a lot at NC, but I think there is a hope for actually delivering something that can benefit all three branches. Like things starts to fall into places. Okay, so the first let's start with a brief introduction. What do I mean by a learning system? And the learning system is it is a dynamical system. And yes, if you have any questions, just stop, interrupt me. This is not an official presentation. It's just a journal club meeting, so it's supposed to be there's supposed to be free discussions. So it's a general dynamical system. There are three types of dynamics: boundary, activation, and learning. The main emphasis today will be on learning, but nevertheless, let's see how those three types of dynamics appear in different types of systems. So in machine learning, by boundary dynamics is what we call a data set dynamics. And now activation dynamics is the activation of how the information propagates through the system, through the neural network, for example. And then the learning dynamics is adjusting your trainable variables or parameters to minimize some suitably defined loss function. Now, in biology, we also have something similar. We have data set plays the role of the environment for a given organism. Activation is how the information is propagated through the organism, how organism receives information, and what the organism does with it. And then the learning dynamics can be um, modeled on different scales. So one example is genotypes, how genes change and how that changes how a given system can survive in the environment. So we have that as well. Now in physics, it's a bit trickier because the learning framework is not the framework we are used to. We do have boundary dynamics. We have to specify boundary conditions whenever we're trying to solve any kind of problem, but there isn't a widely accepted understanding of what would be activation or what would be learning dynamics. Now, there are some answers that have been proposed in the literature. The analytical answer would be that trainable variables could represent, for example, values of fields. Non-trainable variables can represent the conjugate variables or in a quantum description, like complex phase. Recently there were numerical studies that Yaroslav and I just submitted to Archive again last week, showing that the positions of nuclei seem to be a good variable, trainable variable describing the system. So this whole thing can be viewed through this prism of physics learning duality. Uh, which means given a system, how am I going to model it? Am I going to model it using physics, and then view learning as some kind of emergent phenomena in certain limit, or maybe other way around? You can view learning as a fundamental description of how the system works, and then physics as we know it, whether classical or quantum, is an emergent phenomena only in certain limits. So here in this talk, I'll assume that take the unusual approach and say, okay, well, let's assume that learning is fundamental and see what comes out of it. Okay, so now since learning will be our starting point, let's review what learning is in context of the machine learning, because there we can define it very precisely. All three types of dynamics, and again, I'll repeat myself, but boundary dynamics, I mean a data set. But I also more generally would mean coupling of the data set to the actual neural network. And that coupling can be the trainable or non-trainable via encoder or decoder. So those are technical details that will not influence the conclusions that we're going to make here. Now, the activation dynamics is propagation through the neural network, usually describe this equation one, where you have a state of this, what I call non-trainable states of neurons, how it changes with time. Now here I'll be careful and I say that yes, it is a discrete time step, but let's call the time that associated with activation dynamics as tau sub a. It can be set to one or something else can be set to one. And then we have this xi as non-trainable variables, and then we have also q mu's as trainable variables, and those can be like components of the weight matrix or something more general than that. And now we come to equation number two, where how does the learning work? How does the learning dynamic works? And we'll take the approach here that it is described by covariant gradient descent equation number two. That's something we uh, published two weeks ago with Mitri. Now we wrote similar equations even before. It is different from what people write in machine learning community, but we think this is important to keep things covariant, right? So usually they would not write any metric in the middle, and they would have the same indices for mu and nu, and that would be the limit if this G mu nu metric would be like Kronecker delta. Now, however, this description wouldn't be very invariant, and so you wouldn't be able to easily go between different coordinate system, as we've argued with in the paper with Katya. So it's important to keep things covariant, and so I'll keep this metric here. Now, one new ingredient here that generalizes of what usually people mean in the gradient descent method is that this G mu nu can also depend on Q in such a way that you cannot get rid of it. You cannot just change coordinates to get rid of Q. So that's would be the limit we are interested here. Um, Now, where does this G mu nu appears will become apparent on the next slide, but for now, this is just how we define it. And then it's important to separate the timescales for those three types of dynamics. We have a boundary dynamics that is greater than the activation dynamics or single step of activation dynamics. And in this sense, we have, for example, if we have a deep neural network, it will take you L steps of the activation dynamics before you reach the output layer, and then you want to change your boundaries through the data set using the data set again. And so there is this separation of scales here. There's also separation of scales from the learning dynamics that you can have. And you can have, for example, a mini batch of size M, and you can take few steps of the changing the boundaries, figure out how your network performs on different data from the data set, and only then change your variables. And so there's this TL. Now, since we're interested in learning dynamics, we'll set this TL equals to 1. And as we will see, we'll actually consider timescales even larger than that for certain appropriate descriptions. Okay, so any questions about that? No questions, let me continue. So now the idea is to analyze this system in different limits. And so the first limit is a stochastic description. By stochastic, we say, okay, yes, there's a loss function, but maybe we can separate it in two parts. One part is where you have u depending only on trainable variables, which can change with time themselves. So there is time dependence here, but it's implicit, not explicit. And then there is additional term with explicit time dependence. And so given those two terms, we will say, okay, let's assume that the second term is like noise. And as a noise, we will choose it to be Gaussian. And so we'll say, okay, let it have zero mean and some variance given by some function C. Now, if that's the case, then the gradient descent equation can be rewritten as a Langevin equation, number 4, which looks very similar to what you had here, but now H is just separated in two parts, in the non-noisy part, the average part, and then the noise. And the noise is, of course, defined through this stochastic component. Okay, so given the Langevin equation, you can derive Fokker-Planck equation. So Langevin tells you how things evolve for individual trajectories, and you have this noisy part. Now, in the Fokker-Planck equation, you are thinking about probability distribution. How does the probability distribution in the space of trainable variables evolves. And if you carry these calculations through, you will uncover some interesting result that there is this G mu here, but then there is also this kappa mu there. And the kappa mu, I didn't write the formula explicitly, but actually it's if you take the C and differentiate it with respect to Q and then with respect to Q prime, so you will get a covariance matrix. Basically, will be a covariance matrix of this noise. So you have at the same time both terms appearing, right? Uh, and this you can view it as anisotropic diffusion, right? So you have a diffusion, but you also have this a diffusion term. This second term has a second derivative with respect to a probability distribution, but it can have different. It doesn't have to be proportional to Kronecker delta. Now, however, there are interesting limits taken for this kappa and G, which are useful in machine learning, and which says that these two things are not independent. And that's kind of important point here that we've showed a couple of weeks ago with Dmitry. Then there are certain you can view like well-known algorithms like Adam, or actually closer Adam believe, or closer to what we wrote it. That corresponds to the power of 1/2. So if you take this covariance matrix raised to the power of 1/2, or take a square root, and then set your metric to be that, now that will correspond to actually what turns out to be a very efficient learning algorithm. We'll discuss it why that's the case, but and then a limit of a equals to 0 when the metric basically is flat, and that corresponds to stochastic gradient descent. And then the third limit, interesting limit that we'll discuss, is when a equals 1, it corresponds to a natural gradient, which isn't as good as in terms of learning than the other two, but yet it has important implications, as we will see. And maybe it is good for certain tasks and something we will look into. So to summarize, we have this Fokker-Planck equation and then three different limits. And there seems to all three limits describe something interesting about the system. In particular, the middle one gives us something that you can experimentally verify. You can just go into your computer, code it and see that yes, with G set it as square root of kappa, the system learns certain learning tasks faster. Okay, now that is what's happening on large time scales. Now let's see what can happen on the shorter time scales. And for shorter time scales, you have to study individual trajectories. Individual trajectories, of course, are harder to study, but what we'll try to do, we'll say, okay, we'll still keep track of this probability distribution P, but we'll try to keep more track of this noise, not just at the level of covariance matrix, but we'll try to follow it more closely, this noise. That's the idea. And it should be valid on somewhat smaller time scales. So if you do that, then the question is, okay, so you're trying to figure out how the probability distribution will evolve and how this noise will evolve. And you can only do that using some principle and putting some constraints. So the principle we're going to use here is called the maximum entropy, stationary entropy production principle, which is a generalization of the maximum entropy principle to trajectories as opposed to states. And the constraints we're going to put here is on the average loss as opposed to the change of the average loss as opposed to the average loss or average energy as in the stationary case. Now, there is one more condition that we'll have to impose to make equations simpler, meaning that we only assume that those fluctuations are anthropic. They're only fluctuating in the direction orthogonal to the gradient. And if you do that, then the change in the loss can be expressed this way, where you have separate terms that all depend only on phi and only on u. And by constraint, we just set it to be equal to some constant. That's what constraint. It's again equivalent to how you would derive canonical ensemble in physics or in machine learning for distribution of states as opposed to the distribution of trajectories. Well, to make the long story short, you set up your variational principle, which I skip many steps here, and you will arrive at the two equations, 8 and 9. And those are the two equations that describes how probability distribution and how this noise function evolve with time. And they are known, very well known equations, but they are only known when this parameter a from the previous slide is equal to 1. So in this natural gradient limit, when g is set to kappa, when both terms, basically, if you set g to kappa, then this g will cancel with minus g, and then you will have a legitimate isotropic diffusion equation. So in this limit, this more microscopic view will tell you that those are the two equations by which things will evolve. Now you can probably see that the equation 8 looks like a continuity equation with appropriately defined velocity. And the second equation is something that is known the quantum Hamiltonian Jacobi equation. Both equations emerge in this certain limit. They in a way they're similar to the Schrodinger equations, as I will argue. So they are similar to the description that you can get from the quantum physics, but they're not the same. There is an important difference, which I'll talk about now. But anyways, from the point of view of the dynamics, we have these two dynamical equations, and we know how the P evolves with the velocity field, right, defined by this, and then how field evolves according to this. Now, there is new quantity here, V, which didn't appear anywhere. Oh, sorry, yeah, V and Q, so which didn't appear anywhere else. Q has an expression through called the quantum potential. You can actually write it, but I don't have an expression for it here, but I will later. But anyways, you have this effective potential now. So interesting. So now in this quantum-like description, or the Mandelung description, the potential is built out of the loss function, but it isn't exactly the loss function. So if you want to equate them, it's not quite right. However, in the limit when u is quadratic, you will see that the second term will be just constant, and this term will still be quadratic. So in the quadratic limit, yes, both u and v are quadratic. And the quadratic limit is the simplest limit, non-trivial limit that we like to analyze in physics because it gives us nice solutions like to harmonic oscillator, things like that. Okay, so they are related, they're not the same. Okay, and now this crucial step, again, we've done it before here, it was done in a covariant way, that the wave function, if we say, okay, let's now just call this quantity a wave function, which has both components. It has this P probability distribution and phi associated with the noise and the loss function. Let's clump them together and define this wave function. Now, what will this wave function in quotation mark will satisfy? Well, it turns out it will satisfy the Schrodinger equation, but as you see, there is something that we've done which we have to keep careful about. Once we do that, a shift in phi by 2 pi h bar should be unobservable, basically, because the wave function will not change. Phi will change, P will change, and so you can observe that at the level of the equations 8 and 9, but the wave function will not change. And to make sure that it doesn't change, you should introduce as discrete symmetry into the system. So somehow your phi shouldn't matter for the learning system on that in that description, that level of macroscopic description. It shouldn't matter whether you add 2 pi h bar to it. Now recall 2 pi h bar in terms of in physical context is just equal to h, the Planck constant. And basically what we are saying in this effective quantum description, shifting your phase by h shouldn't matter. Now, but phi it comes from the noisy term in the loss function. And so what we are saying here, you should have a system where adding or subtracting some discrete value to it of a certain size of h shouldn't matter. And you can think about this as having a neural network where you've defined a bulk loss for each neuron, and there is kind of cost for each neuron to be in the system in terms of the loss. So yeah, you can have more neurons, but that kind of cost you something. So in this setup, this is the right shift, and then you will end up with you can end up with this such a loss function will can end up with dynamics, which is effectively described by the Schrodinger equation. So it's one interesting limit that you get in this in the for a equals one. Okay, so to make let's move on. So now we want to take and that's how physics fits in into this, at least quantum physics fits in into this framework. For the classical physics, there are other papers that I can refer to, or you can look at the last paper with Yaroslav, where we show that actually at the limit of large time scales, the stochastic gradient descent turns into the second law. And this is kind of second Newton's law. This is the simplest way for you to see how the classical physics emerges. Okay, but let's look at the biology, and let's set up evolution that is pretty common in modeling biology. We are saying, okay, so we have dynamics where things change by discrete jumps, and then by the acceptance. So for example, you can have a what's called a genetic drift in your genotype space of organisms, and then some of those are selected and some of them is not, and so you have some acceptance probability. You have this product of two probabilities that tells you whether you will make a transition from some state Q to state Q prime. Now, you can also recall that this type of setup is present um, uh, in the algorithms, Metropolis or Kawasaki algorithms, where you're trying to find you're trying to generate a state given by some distribution. So it's somewhat different task here. We're actually discussing the evolution. We are not using it to generate a random sample from some distribution, but to actually describe the dynamics. Okay, and so let's consider a simple limit where this acceptance probability given by sigmoid. Now it's again different from what you use in Metropolis algorithm, but it's a smooth enough function. It's first of all, it's close to the function used in Metropolis algorithm, but it's smooth enough that allows us to do differentiation and integrations that will follow. Okay, and then we say that, okay, and let's the equilibrium distribution given by some canonical ensemble. We don't know what it is, but it's we take it to be given by this minus beta h, where h is in machine learning it would be again loss function. Here it is the log of the fitness in context of biology. So this exponent to e to h, it would be like fitness. Okay, so then the idea here is saying, okay, so let's we want to find describe this evolution, and we impose something that's called a detailed balance condition, which is described by equation 15. And then you can ask the question, well, does this acceptance probability satisfy the detailed balance condition? And the answer is yes. So Metropolis uses a different function for the very same reason, because it will satisfy the detailed balance condition for this equilibrium distribution. Okay, so now to proceed, we already set up with our acceptance probability through this sigmoid function, which is like shifted hyperbolic tangent, shifted up. But let's now describe the probability of jumps. So when we describe it as a Gaussian, which again, the simplest thing with zero mean and this covariance matrix. Now, once you do follow some steps of mathematics, you can show that if you do that, then the dynamics of average trajectory, so it will be all stochastic, they'll be jumping around and stuff, but the dynamics of the average trajectory will satisfy equation number 17. So note that this C mu nu, which was a covariance matrix, plays the role of the inverse metric that we had in the gradient descent. So it shows that this type of evolution, you can call it neuroevolution, you can call it Metropolis evolution, or I just call it biological dynamics. This type of evolution is described by this gradient descent equation. Okay, but this is we've already done some coarse graining, but not the coarse graining that we have done on the previous slides. We have replaced this with the with a Fokker-Planck or with Hamilton-Jacobi equation. And to do that, we have to increase our time scales, right? So to go from this, we again have to take this h and separate into two parts. Let's assume this h has time-independent part and then time-dependent part, which represents noise. And if you do all that, basically you will end up having a Fokker-Planck equation that is written here. Now, it's another important thing that I've skipped on. It's number 18. Basically, this C mu nu, yes, it's inverse metric, but it doesn't depend on Q, on position. And because it doesn't depend on the metric, we can just get rid of it. We can just perform certain transformation, coordinate transformation, and in this new variables, the metric will be just proportional to delta mu nu. So that corresponds to the limit of a equals to 0. Again, in this machine learning setup. Remember, for a equals 1, we recover Schrodinger equation or quantum regime, at least if there is this discrete shift symmetry. Now here, because of the simplicity of the model that is usually used in the neuroevolution or in the biological evolution, we recover the limit of a equals to 0. Now, on longer time scales, you can set up a Schrodinger Fokker-Planck equation, which is given by that. Okay, so now let's move on. So we've already considered two limits, but let's be more general. Let's say, okay, so let's see what happens in general. In general, when we keep G, the metric, and kappa as two separate objects. And if you do that, you follow all of the derivations, and you can do it at the microscopic scale using this maximum stationary principle of stationary entropy production, or you can do it at a more macroscopic scale using Fokker-Planck equation. But let's concentrate on this smaller scales. On the smaller scales, you will recover, which I call here a neural Hamilton-Jacobi equation. It's kind of similar to what you got in the a equals 1 case, but now without a setting to be equal to 1. And so I call it like neural Hamilton-Jacobi equation. And something that's usually called a quantum potential that appears here, I'll call a neural potential. It has an explicit dependence of kappa mu nu. So usually this object, denoted with Q, has G mu nu here. So in here, it's a separate object. It doesn't have to be related to, it doesn't have to be G mu nu. Moreover, we know that in effective learning algorithms, it isn't. It isn't G mu nu, it's actually square root. It's a square of G mu nu, right? This kappa with the low indices. Also, be careful when I write upper indices for any tensors. It means that I have raised those indices with the metric G mu nu. Okay, so that means this object here means you have two matrices G mu nu with raised indices, and in between matrix with low indices. Okay, so yes, so in general, it will not be a quantum potential, and for this interesting case of a equals 1/2 corresponding to the efficient learning, this is how it will look. So it will actually remove this. What in quantum case you have G mu nu here, it will get rid of it and it will put a delta mu nu here. So that's now what does it do to a system? Putting a delta mu nu here, like if you're trying to look at all of the trajectories in the trainable space, it's actually interesting, and actually just shows why this choice. I call it Adam belief or Adam choice. Of course, they're not working with matrices; they are working only with diagonal part of the matrix. At least Adam belief. Adam doesn't even work with that because they have they're only looking at the covariance matrix of the gradients of the loss function without subtracting the means, right? So, but anyways, those are technicalities. Now, the reason why this works can be seen here. Why it works so well is because if you look at your noise covariance and you say, okay, all I want, because I don't know which value a given trainable variable should take. So since I don't know anything, I should just make this noise covariance to be isotropic. I have no knowledge about it. And in order for it to be isotropic, in order for this covariance to be proportional to delta function, Kronecker delta, you do need kappa to be given by G to be given by a square root of kappa, and then those two G's will cancel with kappa, and you'll have a delta. So the choice is about just telling, well, I don't know something about the system. As if I don't know, I don't make any assumptions. And so let's all trainable variables evolve with the same covariance. And that's great in the early stages when you don't when you haven't reached any good solution. But once you start reaching it, once you see that certain variables start stabilizing, or they stop fluctuating as much, you should change your regime. Okay. And if you don't change your regime, then the system will never find a good, well, at least it will find a good state solution, and then it will go away from it. And for that to happen, you need to switch to a new regime. And this is the regime described by this flat metric, or a equals to zero. So this is a is equal to 1/2, a equals to zero. I will get back to that, how it's realized in those algorithms shortly. But anyways, so in this general case, in this case you will describe the evolution can be described also more macroscopically, not at the level of the Fokker-Planck equation, by this. And then you see here that there is again a difference in the Hamiltonian Jacobi equation that you get, because you get this delta function here where usually kappa would appear. Okay, so and this flat space limit, the whole point is that very well it finds it actually corresponds also to the limit of stochastic gradient descent, which works very well when you are not too far from the solution. But if you are far away, it's better first start with a equals to 1/2, and then only later, once you get closer and your fluctuations are decreased, switch to a equals to zero. Okay, so now let's try to study the complex systems, and like first summarize what we have. But we know that at a equals 1 regime, there is some sense in which quantum dynamics emerges, which will probably allow you some like kind of quantum leaps, and there may be some way for you to adjust your learning dynamics such that the efficiency of quantum algorithm become important. I don't know that yet, but that's just a kind of conjecture. We do know numerically that this is a good regime, and then we know this is how it stabilizes. And that is the reason why in the algorithms like Adam or Adam belief, they have this small addition to your covariance matrix. It's condition, it's exactly for that. It's once your fluctuation becomes small, you want to switch to the a equals 0 regime from a equals 1. And if you define your metric as a square root of this small term proportional to identity times plus kappa, then it will interpolate between both regimes. When kappa is small, it will be just identity. When kappa is large, it will be a square root of k. Great. So you have both regimes. Now it doesn't have this a equals 1 regime. No, first of all, we don't know how to effectively use this equal 1 regime, but if this conjecture is correct and quantumness can be used, then we somehow want to incorporate this third regime as well. And here's an example of how you can do that. You can just put under square root 3 terms, constant, linear, and quadratic. And then, when you study it, you will see that there will be a range of scales. There may be a range of scales where this middle term plays in effect, but sometimes you may have no such, so there are two limits. So in this one, you will have no middle range. Basically, it's either first dominates or last dominates. In this other regime, you have a range of scales. So you can think about this. There may be a regime where there is no effective learning, call it like physics regime in quotation mark. And then there is phase transition takes place where you do have this efficient learning. And then things start behave very different from physics, and you see this square root of kappa behavior. And so attempting to interpret this phase transition as appearance of complexity. Of course, for that, whatever learning system should be able to adjust those parameters. So it's not something that without the ability to adjust these parameters can emerge. So it has to be at the level of the algorithm of a learning system, whether it is organism or physical system or whatever. Okay, so let me conclude like main results. The main results that on the very large time scales, you can describe everything with a Fokker-Planck equation, but there will be G mu nu and kappa mu nu, and kappa mu nu will be like anisotropic Fokker-Planck equation, very important. Now, on the shorter time scales, there is a more fine-grained description using this neural Hamiltonian Jacobi equation, which in certain limits is identical to quantum Hamiltonian Jacobi equation, which in certain limits is identical to the Schrodinger equation when you have um, symmetry in the shift. Now there are three different regimes, and again, we're just starting to understand their significance. For machine learning, we know the significance of the last two. We don't know the significance of the first. In physics, we know the significance of this first and the last, but we don't know the significance on the middle. In biology, it's only the last one. In modeling biology, only the last one is used and not the first two. So there's a lot of ways to explore and see, how those regimes can be realized. One observation that you can actually incorporate all three things together, but then you should be looking for some kind of phase transition, which will go from a system described only maybe by two regimes to be described by the third. And so in terms of biological evolution, this actually tells you something interesting, that if biological system want to evolve using this, changing A or G, which is depends on kappa, if they do want to do that, they have to keep track of the previous changes or previous mutations. And it's not like, all you know about the system is where you're right now. You should also have a knowledge of history of bad and good mutations, and you want to use all that history to decide, where mutations should be suppressed or where it should be and I should rewarded. And so in this sense, biologists try to say that evolution is a survival of the fittest, but here you would also say actually it's also of the smartest, those who actually have the mechanism to memorize and at least statistically the information about past mutation. All right, I'm done with this talk. So if there are any questions, I'll be more than happy to answer.
I had a question.
Okay, go ahead.
So can you actually describe, let's say, some sort of, emergence of non-unitarity in Schrodinger's equation using this formalism?
Yeah, it should be. I think you're right. So unitarity is only comes with this restrictions
Yes.
with
Yes.
A equals one and the shift symmetry. So once any of those are violated, yes, you should expect to see some, and I would expect to see it in a complex system. So because if it's a very simple system, then it will be either in the regime A equals to either it will be A equals one and it's quantum mechanics, or n a equals to zero, and then everything is flat space, so you would not distinguish anything from classical. But
Yes.
if the system can actually go through different regimes, and especially this intermediate regime, then you may have, from the quantum point of view, it will mean that things are non-unitary. Absolutely. Yeah.
And also, I mean, can you design better simulation algorithms for Schrodinger equation like you did for molecular dynamics, right?
That's
Using
right.
this.
That's right. So that's another thing, right? So if you can trick and have an effectively quantum evolution by just using classical learning dynamics, then yeah, oh,
Yes.
absolutely, yeah. And not only that, I mean, I think bigger, right? So you can implement this A equals one within your algorithms, and maybe it's useful at a very early stage, okay? Like let's say the stage of identifying what is the right architecture for the neural network. Okay, so at that stage,
Yes.
it may be good to have a cool one, have quantum leaps going around everywhere. And that's why we know that quantum annealing works so well, because it doesn't get stuck anywhere. So yeah, so
Yes.
there's a lot to think about. Yeah.
Thank you.
Uh, so I was confused about the shifting symmetry thing. So is
Yeah,
that
I
a thing
went
that
through
you
this
have?
very fast. Yeah. Yeah.
But so is that an imposition that you put there so it works, or does that come from
Okay.
A value
So,
that you
so,
chose to
so
make the
first of all,
shifting?
I skipped over it because it was discussed in our paper with Kasnelson a few years ago. That's my but however, it's very important that you should have that symmetry. And if you don't have that symmetry, if you do not have this shift symmetry, then the system is not described by Schrodinger equation. It's described by the Mandelung equation. So then you do not have interpretation for this phi as a phase, because phase is different with just real number. Real number can go from minus infinity to plus infinity. Phase in the other case goes from 0 to 2 pi. Yes, and then it comes back to where it started. So it's kind of there is this symmetry, and if you don't have that, you're screwed. It's not a Schrodinger dynamics. Now here, what being said is that well, you can have that symmetry in the definition of the loss function, either fundamentally, like a loss function is such that it costs you to have another neuron, like have more, or it's something that emerges from the dynamics. Then neurons either get connected or disconnected, and once they connected, they suddenly like loss function increase or decrease.
I
Um,
see.
so it's a subtle issue, but without it, there is no quantum. So
Yeah.
without this, there is Mandelung, but there is no Schrodinger.
All right.
Sure. Thank you. Okay. Any other questions? All right. Well, if there are any other questions, you can always post later. I did go through this very fast because I had to cover a lot, but I hope some of it made sense. And well, thanks everyone for coming. I'll see you next week.